Okay, so since we've introduced this new measure of complexity, before we go and prove things about it, let's do some examples. Okay, so, and we're going to focus on now infinite hypothesis sets because, that's where we're trying to go. So let's consider the perceptron in 2 dimensions. Okay, our favorite number of dimensions, our favorite hypothesis set. Perceptron in 2 dimensions. Okay, so, let's consider, 3 points. Okay, and x1, x2, x3. And I'm trying to indicate that these 3 points are on a line. Okay. So, let's list the dichotomies. So what does a perceptron do? A perceptron places a line and separates. Okay. So let's list the dichotomies that can be implemented. Well, I can place the line so that it's somewhere here, so everything is plus. I can place the line here so that this is minus and 2 plus. I can place the line here, somewhere here, so that this is 2 plus and minus. I can place it here so that, everything is minus. So what are the dichotomies that I can implement? Let's see. I can implement plus, plus, plus. I put the line here. I can implement minus, plus, plus. I put the line here. Okay, I can and that side is plus. I can implement, minus, minus, plus, minus, minus, plus. If I put the line here. Okay, I can implement minus, minus, minus. Okay, and is that it? No, because those were all the perceptrons which were plus in that direction. What about if it was minus in that direction and plus in this direction? Okay, so if I put the line here and it's minus in that direction, that's minus, minus, minus. I already have that. If I put the line here, minus in that direction, I get plus, minus, minus. If I put the line here with minus in that direction, I get plus, plus, minus. If I put the line here with minus in that direction, okay, it's minus, minus, minus. And you will observe, very nice. Okay, that now I have 1, 2, 3, 4, 5, 6 dichotomies that I can implement. What am I missing? Okay, what I'm missing are minus, plus, minus. So I'm missing, I don't have, let me put it in red, I don't have, minus, plus, minus, and I don't have plus, minus, plus. Okay, so what about these guys? So let me show you what that looks like. Minus, plus, minus. Okay, this dichotomy. Okay, well, how am I going to put the line to get this dichotomy? So, let's say I do this and I need, so if the minus is under here, then I need to somehow turn the line and get that minus under the line. But once I get close enough to that point, this blue starts getting classified as minus. So I cannot implement. Okay, so these cannot be implemented. Okay, that's fine. So that just means that h of x1, x2, x3. So h of x1, x2, x3 in size. So the complexity of the perceptron hypothesis set for this set of points is 6. Okay. Now I'm going to take you back to the worst case analysis that we talked about. We didn't define this as the true complexity of h with respect to data sets of size 3. Okay, because with respect to data sets of size 3, I get to choose the data set. Okay, and I must choose the data set to make this size as large as possible. And I very, cheekily chose these 3 points specifically to illustrate that if you choose the points badly, you won't be able to implement as many dichotomies as you think you should, because it seems like we should be able to implement 8 dichotomies. Remember that bound 2 to the n? Okay, so, let's change the points and see if we can do better. And indeed, look. If I place the points like this, okay, now, plus, 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 I just put the line here. Minus, plus, plus, I put the line here. Minus, 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 I put minus, minus, plus, I put the line here with that side being minus. Minus, 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 I can just put the line here with that side being minus. Okay, plus, minus, minus. So plus, minus, minus. I put the line here with that side being minus. That side is minus. Okay. Plus plus minus, so plus minus, put the line here with that side being plus. Okay, now, but here are the interesting ones. Minus plus minus, minus plus minus. Okay, all I did was move this point that was on the line, I moved it down. But now look, minus plus minus. Okay, so this guy, minus, and that's plus. No problem, put the line here. So making those points collinear was a bad idea. Okay. Now, indeed, I can implement, minus plus minus and plus minus plus. So I can implement them. I can do minus plus minus and plus minus plus. And so now I have 8 dichotomies. And I know I cannot do more because there are at most 8 dichotomies. So m sub h of 3. The maximum number of dichotomies that I can do, if I'm allowed to choose the points to try to maximize, is indeed 8. And remember, we had that bound 2 to the n. Nice. Okay, the bound is working. And indeed, this hypothesis set we might have guessed. It's such a complicated hypothesis set. If you allow me to choose the points, I'm going to be able to implement all 8 dichotomies because, I've got infinitely many hypotheses to choose from. Okay, so let's do another example. Okay, same, 2-dimensional perceptron. Let's increase to n equals 4. So n equals 4. 1, 2. Now we know we shouldn't choose the points to be in a line, so let's choose them, somehow randomly. Okay, and remember, so now I'm going to jump straight. Remember that when we had 3 points, the dichotomy that was hard for us to implement was that sort of alternating dichotomy, minus plus minus. So let me jump straight and see if I can implement the alternating dichotomy here. Because if I can implement that alternating dichotomy here, odds are I can implement all the other ones. Okay, so let's go for the alternating dichotomy. Plus, minus, plus, minus. Okay, so these two guys are minus. Sometimes this is called the XOR type of dichotomy. Forget about, what we call it. Okay, it's alternating. Challenge. You figure out the perceptron that implements this. So figure out a line that separates the plus points from the minus points. Okay, so this is the dichotomy, plus, minus, plus, minus. If I label these points x1, x2, x3, x4. It cannot be done. Okay, because if I try to get these two as plus, so I need to put my line somewhere here, okay, with that side as plus, you're going to get that point also as plus. Or if I put my line here with that side as plus, I'm going to get that point also as plus. You cannot implement. You cannot implement. Okay, and what about the flipped one, where it's alternating but starting with minus, plus, minus, plus. So minus, plus, minus, plus. You cannot do that either. So this one you cannot do. This one you cannot do. Okay. Now you might think, well, did I choose the point specially? So now this is a challenge for you. Go, try to find 4 points. And I claim that this is for this arrangement of points is the arrangement for which you can do the most. Okay. And you cannot do these two. Just cannot. Okay. And it doesn't matter how you arrange the points. So this means that for the perceptron, m sub h of 4 is equal to 14. And that is less than 2 to the n. There is hope. Remember we said that, 2 to the n is not so useful in the bound. Okay? But we have some hope now that, even for an infinite hypothesis set, okay, in some sense, this infinite hypothesis set, which is the perceptron, from the perspective of complexity, it's not that complex as we thought. Because look, 4 points can reveal a deficiency. Okay, 4 points alone reveal a deficiency. So what this means is that no matter where you place your 4 points, you're not going to be able to implement more than 14 dichotomies, which is less than that upper bound, which we already argued. This upper bound of 2 to the n is not going to be much use to us, but there is hope. So it looks like at least hope for the perceptron. Okay, that its effective complexity is not as bad as it could have been. It's much better. Okay. Let's consider another example. The one-dimensional positive ray. Okay, so I'll tell you what the hypothesis looks like. So we're in one dimension. Okay, and the hypothesis, so h of x, the hypothesis in this set is of the form sine of x minus w0. So it's similar to a perceptron, except that the perceptron would have had, w1 x, plus w0. This is, you can think of this as I've set w1 to 1, and the fact that this is minus w0 is just convenient. Okay, it could have been plus w0. Okay, but this has the interpretation that you pick a threshold w0, and on the right of the threshold you are plus 1, and on the left you are minus 1. So that's why we call it the positive rate. Okay, so let's place some points, and this time we're going to go all out. I'm not going to consider 3 or 4. We're going to go all out and place n points. Okay, so n points. Okay, so think of this as x1, x2, x3, x4, xn. Okay. Now, in this example, I've placed w0 here. Okay, and so what that accomplishes is everything, all the points on the right here are getting classified as plus. Okay, and all the points on the left are getting classified as minus. Okay. And it should be sort of, with a little bit of thought, you should be able to convince yourself that, all I can do is change the position of the threshold, and that'll change how many of the points get plus by defining how many are on the right of the threshold. And effectively, there are only, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, different regions in which I can place the threshold. If I have n points, there are actually n plus 1 regions. So here I get all plus. Here I get all minus, and then I can get some combination of left red and right blue by placing the threshold in these intervals. Okay, but since there are only n plus 1 different, since there are only effectively n plus 1 useful positions for this W0, there are effectively only n plus 1 different hypotheses in this uncountably infinite hypothesis set. Okay. So in this case, we can explicitly count the number of dichotomies that can be implemented, okay, and the number of dichotomies that can be implemented. So and you cannot get a better arrangement of points to increase that number of dichotomies. So the max number of dichotomies is equal to the number of different regions where I can place W0 is the number of different regions where I can place W0, and that's equal to n plus 1. So m sub h of n is equal to n plus 1. So let's compute, when n equals, so let's do n here, and m sub h of n. Okay, so when n equals 1, 2, 3, 4, and so on. So m sub h of n is n plus 1, so it's 2. Okay, and 2 is the same as 2 to the 1, so it accomplishes the bound that we had before. But now, the moment I get to 2 here, n plus 1 is 3, and it's already less than 2 to the 2. Okay, 2 to the 2, which is 2 to the n. Okay, and here we have 4, here we have 5, and so on. Let me just write here 2 to the n, which is, remember, this trivial bound is 2, 4, 8, 16. Okay. And now you can see, there's a lot of hope for this hypothesis set in one dimension. Even though it's uncountably infinite, it's not as diverse as it looks, because on a data set of size 4, it can only implement 5 dichotomies. Only implement 5 dichotomies. When in theory, if it were really that complicated, it should have been able to implement 16 dichotomies. So this is just to show you that this measure of complexity, this effective number of hypotheses, is quite beautiful. It's a very imaginative step in analyzing the sort of complexity of a hypothesis set when what you care about is a data set. That even though in the most complex hypothesis on 4 data points should be able to implement 16, this guy can only implement 5, which is much less now than 2 to the n. So there is hope, okay, that this measure of complexity will be useful when we plug it into the bound. Okay, so I want to show you, now I want to illustrate, 2 things here. So in this case, we could compute m sub h of n, exactly. In this case, we computed it sort of by hand. Again, we showed that it's 8, so m sub h of 3 in this case was 8, which is equal to 2 to the n. So let's put that same table. So, when you have n and m sub h of n, So it turns out that if you have 2 points, or if you have 1 point, you can implement both dichotomies. If you have 2 points, you can implement both dichotomies. If you have 3 points, you can implement both dichotomies. I mean, all 8 dichotomies, if you suitably place them. But if you have 4 points, you can only implement 14 dichotomies. Okay? And if I put here 2 to the n for comparison, this is 2, this is 4, this is 8, this is 16. Okay? So I will put this in red here. Da, 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 to show that, there's hope in this hypothesis set. It's not as complex as the most complex diverse hypothesis set could be. And we say that this hypothesis set gets broken. We see its deficiency at n equals 4. And this hypothesis set gets broken at n equals 2. Okay? This hypothesis set gets broken at n equals 2. So in some sense you might think, well, this hypothesis set keeps chugging along, so it seems a little bit more complex. Okay, and only gets broken at n equals 4. This hypothesis set gets broken at n equals 2. So in some sense, this seems like a less complicated, less diverse hypothesis set than this. Okay. So let me consider one more example. So in this case, we can sort of we've computed it. Okay, and we might ask, what about n equals 4? What about n equals 5? Question mark. Okay, the maximum we know is 32, but what is it? Well, we can go ahead and compute it, and if you want an interesting combinatorial exercise, try to compute the number of dichotomies that the perceptron can implement on 5 data points, where you get to choose the data points, so as to maximize that number. Okay, here we computed it exactly, and in some cases, it's hard to compute exactly, but we can show this situation does occur in some cases, okay? So it's hard to compute the exact value. Here we computed the exact value is 14, okay? The exact value is 14, no problem. And we see that it's broken, okay? But in this case, it's hard to compute the exact value. I can tell you for sure that it is less than 32. Okay, I can tell you for sure that it is less than 32. And you might try to think, what's the argument to show that it has to be less than 32? And it has to do with the fact that on 16 points, you can only do 14. I'm sorry, on 4 points, you can only do 14. Okay. Let's do another example. So 2 dimensions, positive, axis, align, rectangle. Okay, now rather than give you so in this case, the h of x is equal to the sine of, w transpose x, where you have w0, w1, w2. Here there's only a w0 because it's just a positive ray. Rather than give you a formula for h of x, let me just illustrate. Okay, so we're in 2 dimensions, and remember now I'm gonna dig into the what does a hypothesis do? What does a classifier do? It separates the region into plus and minus. And so what we mean here is that you have an axis aligned rectangle, and you can place this anywhere you want with any height and width. Okay, and inside the rectangle it has to be plus, and outside the rectangle is going to be minus. So this is what. So, and all possible hypotheses of this kind belong to this hypothesis set. Again, uncountably many, because you get to choose, for example, you get to choose the bottom left vertex. So there are 2 values, x, y for the bottom, and the top right vertex, x, y. So you get to choose 4 real parameters, and that defines the rectangle. Okay. And inside the rectangle is +1, and outside the rectangle is -1. Okay. So again, let's consider some points. Now let's jump, so 4 points sort of broke this hypothesis set. 2 points broke this hypothesis set. Let's see if 4 points can break that hypothesis set. So let's place 4 points, in 2-dimensional space. So 1, 2, 3, 4. Okay. Now I claim that you give me a dichotomy, any dichotomy you want. So this is a kind of a game I can play to show you that I can implement all the dichotomies. Give me any dichotomy you want, and I can implement it. So let's think of the dichotomy that broke, this guy, the alternating dichotomy. Okay, so the alternating dichotomy looks something like this. Plus, minus, minus. Okay. And I claim no problem. I'll just put my positive rectangle like this. Okay. And I've implemented it. No problem. Okay. And you can arrange any three, plus points and cover it with a rectangle. You can arrange any one plus point and cover it with a rectangle that's just on top of it. All 4 plus points you can cover with a rectangle. And then if there are no plus points, you just put your positive rectangle outside. Okay. So we can implement any dichotomy. So for these 4 points can implement any dichotomy. Okay, so therefore for these 4 points, the effective size of the hypothesis set, in other words, the number of dichotomies you can implement is 16. And since you can never get more than 16, that means that m sub h of 4 is equal to 16. Okay, nice. Okay, so this hypothesis set looks like it's not broken, it's not deficient, it's as complex as it could appear for a set of 14 points. Okay, but what about 5 points? For a set of 4 points, sorry. What about 5 points? Okay, so now let's add a point. So let's take my 4 points. Okay, so let's take my 4 points, and now let's add a point. So where do we want to add the point? I don't know. Let's, it has to be either inside these or outside. What do you want? It doesn't matter. It can be either inside or outside. Okay, so let's imagine the case where it's outside because that looks safer. Okay, so here's a case where it's outside. Okay, and what I'm going to do, because it's outside, I can see, so where did I put it? Did I put it below this point or above this point? If I put it below this point, okay, so let's imagine that it's below this point. It could be above, and the argument is exactly the same. Okay, so you might think, so figure out what the argument is going to be if it's above this point, but let's say it's below this point. So now I'm going to consider these 3 points, okay, and I'm going to consider the dichotomy, which is plus, minus, okay, and I don't care what you pick on those. Okay, why do I not care? Because look, if any positive rectangle is going to include these 2 points, okay, then its top and bottom must sort of, its top and bottom, its top edge and its bottom edge must be its top edge must be above this point and its bottom edge must be above this point. Okay, so its top edge is somewhere here. And its bottom edge has to be somewhere here. And now we can look at the left and right edges. The left edge must be somewhere on this side. And its right edge must be somewhere to the right of that point. Okay, but now we have a problem because any positive rectangle that's going to get these 2 correct is going to mess up that guy. Okay. And in fact, you can show that whenever you have 5 points, there will always be a point that's inside the rectangle defined by 2 other points. And then you can construct a counterexample like this, okay, that cannot be implemented. And so what I'm just proving here is that, with 5 points, so theorem, if you want to call it a theorem, with 5 points, there is always a dichotomy that cannot be implemented. Okay. Now, the specific dichotomy that cannot be implemented depends on the 5 points, but what I know for sure is that with 5 points, there is always a dichotomy that cannot be implemented. Now, I'm going to ask you to go and formally prove that, on your own time. Take it for granted from me, and maybe we'll assign it as an exercise, okay, for the homework. Okay. So, that tells me that, M, so the maximum number of dichotomies sub H for this positive axis-aligned rectangle when you had 4 points was equal to 16. M sub H of 5 points, well, we don't know what it is. Okay. But what I do know is that no matter how you choose the 5 points, you won't be able to implement all 32 dichotomies. So what I know is that this is less than 32. Okay, so it turns out that if I did the same table with n going from 1, 2, 3, 4, 5, 6, and so on. So if I do m sub h of n, you can easily convince yourself that it's 2, 4, 8, 16. 16 we just showed. Okay, m sub h of 5, we don't know. We don't know m sub h of 5. What we do know is that it is less than 32. Now in practice, you could, if you wanted to, you could actually compute m sub h of 5. Okay? And if you feel like it, go for it. Okay? So I'll put this in red. Okay, and just for comparison, let me show you 2 to the n. 2 to the n. It's 2, 4, 8, 16, and 32. Okay? And here it will be 64. Okay? Now here we don't know what it is, but we do know that it is less than 32. So again, hope, even though this is an infinite hypothesis set, it doesn't realize all that complexity on 5 points that it could have. It could have implemented 32 dichotomies, and among infinitely many hypotheses, we just couldn't find a way to implement all 32 dichotomies. Okay, and here it will definitely be less than 64. So we know that it's going to be broken there as well. It's going to look broken. This hypothesis set has gotten broken, has gotten deficient. 4 data points is not sufficient to reveal a deficiency, but 5 is. Okay, 2 data points enough to reveal a deficiency. 4 data points enough to reveal a deficiency. So 2 things to take away. First, infinite hypothesis sets, okay, even though they have uncountably many hypotheses, do not reveal the full range of diversity that is possible when viewed through the lens of points, of data points. Because 4 data points, you should be able to do 16 if you could do anything, but you cannot. You can only do 14. So infinite hypothesis sets do not attain this most complex, diverse upper bound on the number of dichotomies that they could have. Okay, so there is hope for the bound. And the second thing to notice is that, hypothesis sets get broken, okay, and we can compute this measure of complexity, but it looks like a very challenging measure of complexity to compute. And it would be nice if we could get some formulas or something like that. Okay, and in some cases we don't even compute it. We just show that, the hypothesis set is broken. Okay, so it would be nice to have a formula or at least an upper bound, okay, that could tell us, how complex is this hypothesis set? How effectively complex is this hypothesis set? Now, we may not be able to compute its true complexity, like the size of the hypothesis set in the finite case, but we might be able to compute its effective complexity, i.e., we might be able to compute an upper bound. And with respect to that error bar, we are upper bounding E out. So if we can get an upper bound on the complexity, then that's just as good for the error bar. We can plug that into the error bar. Okay. So let me give you the combinatorial puzzle next. Speed erase.